Hi, uh, good evening. So let us start today's session on live session 10. So this session will be on heat treatment process. So as no one has still joined, I will start today's session at as it's already crossed 6:10. You can always access the video, whatever I will go through now. So let us start today's session. So in the first question, it says, which of the following statement is correct regarding the Martensite structure? So the first statement says it produces due to slow cooling rate. Second statement says the structure does have fine grain size. And the third statement says tempering of martensite increases in strength and hardness. Now, if we see, if we try to find out what happens during martensite transformation, we need to always refer to something called TTT curve. So if you see TTT curve, this is basically time, temperature, and transformation curve, right? Now, if we try to find out what happens in FEF3C phase diagram, let us try to draw some schematic of TTT curve in FEF3C. So if this is a time axis, which is in second, and then if it is in temperature, and let's say you are somewhere at eutectoid temperature. So this is I am referring as eutectoid temperature, where my austenitic phase is stable, and from here your transformation starts, and it will follow something like C kind of curve. So let's say this is somewhere it is 100 degree, and the eutectoid temperature somewhere around 720 degree. And if you see you see this region, this temperature is called ms, where ms is martensite start temperature. And there is some temperature where martensite formation ends also. So let's define that as mf. And at certain temperature, which is somewhere around in between 500 to 600, uh, there is some phase formation called bainite formation, and here you will form pearlite formation. Now, to get the martensite structure in steel, you have to have some kind of fast cooling rate. So martensite is basically depends on fast cooling rate. Let's say we are cooling it something like this. It's very rapid. So as you are cooling it very rapidly, so you are not crossing this region, right? So if you see this region, due to so much fast cooling, you are not crossing this C kind of region, and you come up with something called martensite. Now, this martensite is basically have very fine grain size, and it is very much hard in structural property perspective, hard and brittle. So the first statement was telling that it produces due to slow cooling rate. So of course this is false. The structure does have fine grain size. Yes, the structure is having fine grain size due to rapid cooling. And now if you do some kind of heat treatment in martensite, so during heat treatment, martensite is tempered and it can transform to ferrite or carbide. And during tempering, it can reduce the hardness, it can reduce the yield strength, and it will enhance the ductility, right? So in the martensite structure, if you are tempering it, what happens? Your strength or hardness gets reduced and you enhance your ductility, right? So it says tempering of martensite increases in strength and hardness. So this is also false. Okay, great. So let's move to the next question. In question two, we need to match the followings where there are different kinds of heat treatment processes like full annealing, normalizing, spherodizing, tempering, and we need to match with different characteristics of these heat treatment processes. Now, if you see annealing process, basically annealing process has three steps. So if we try to simplify the annealing process, so initially it will be heating the material to a high temperature. So it may be near or above critical temperature, and then the material soaks the temperature. So soaking the material at that temperature until the required material properties are achieved, right? And then we will cool the heated material at a slow rate to the room temperature inside the oven. So it will be basically a furnace cooling. So what happens in annealing? Annealing basically modifies the properties such as machinability, maybe some mechanical or electrical properties, or maybe it enhance the dimensional stability also. Basically, this process softens the material. So annealing consists of heating a material to a high temperature where recrystallization or a phase transformation takes place, and then cooling slowly, often in heat treatment furnace, right? So if we see it here, full annealing is matching to furnace cooling, right? Annealing is basically, as I was saying, soften the material after it has been hardened, right? And cold work or a full anneal gives the very softest of the microstructure. So what happen is basically both the yield strength and tensile strength gets reduced in case of ferritic steels, and also you are enhancing the toughness, right? So your ductility or toughness is getting enhanced. Is my screen visible?
Yes, sir.
Yeah. Okay. Now, in terms of normalizing, in normalizing, what happens is basically Normalizing is done by heating the material to a temperature maybe above its critical temperature, and then the material is soaked at that temperature until the transformation occurs, right? And finally, the heated material is taken out from the oven and cooled to the room temperature outside the oven. So, normalizing process basically enhances the grain size, and it can improve the consistency of microstructure, right? This is a heat treatment. It's mainly carried out on ferritic steels, and yeah. Now, if we try to find out what happens in terms of temperature, uh, in terms of temperature, so if we see the eutectoid portion of the steel, so this is gamma is your alpha is your ferrite structure. It will be alpha plus gamma, so be beta plus gamma. Beta is cementine. This is what percent of carbon, and this is temperature. So basically, what happens during annealing is like if this is your critical temperature, let's say this line, what I am bolding it, this is your upper critical temperature, and this line, this is your lower critical temperature. Now, if you see in terms of composition and temperature, when you are doing some kind of full annealing thing, you are heating the material in this region, and then you do some kind of furnace cooling uh, to enhance the ductility, toughness, and because of that, because of that increase in temperature and then cooling, your hardness can be reduced, right? And then in terms of normalizing, your temperature range is somewhere above that critical temperature. It may be somewhere around 30 to 40 degree more than upper critical temperature. So you end up with somewhere here. So this region is your normalizing region. So in normalizing region, what you do some kind of air cooling, right? And then spherodizing region is somewhere here. So somewhere at lower side of the upper critical temperature. So here you have your spherodizing region. So basically, in spheroidizing, all cementile are in the form of small spheroid, and it disperses throughout this your ferrite matrix, right? And yeah, and if you see this tempering is basically it's always associated with some term which is called quenching. So you always call it quenching and tempering. So what happens is like this: quenching basically comprises a rapid cool from a high temperature, right? So if you see a ferritic steel, this ferritic steel would be heated to above the upper transformation temperature, or whatever I am calling is as upper critical temperature, and above that upper transformation temperature, and then it gets quenched in water or maybe oil or air blast, whatever, to produce a very high strength fine grained martensite, right? And but but if you see these steels, they never used in quenched condition. They are always tempered following this quenching operation. So tempering is basically a heat treatment which is carried out on these ferritic steels at a relatively low temperature. It may be below that lower transformation temperature. In a conventional structural carbon steel, this can be in the region of maybe 600 to 650. So if you see some carbon steel, this tempering range can be 600 to 650 degrees C. So what happens is it basically reduces the hardness a little bit, lowers the tensile strength a little bit, and it improves the ductility and toughness. So in any case, in all your structures, you want both the hardness and ductility, right? So if you are making it too hard, it will be too brittle. So some kind of elongation or ductile behavior you want in your material property. So mostly these normalized steels are tempered before you used, or quenched steels are also tempered condition. So yeah, for spheroidizing it will be Fe3C in small spheres, and this is already matched. Okay. So this is a simple objective question which says that what happens during the Eutectoid reaction. So basically, as I was saying, in your Eutectoid reaction, if you see the phase diagram, you see the phase diagram. If it is what percent of carbon, and this is Fe, and towards the right side, it's increasing the carbon percentage. And I'm taking only the Eutectoid portion. So this is alpha, this is alpha plus gamma, this is gamma, this is beta plus gamma, this is alpha plus beta. What is alpha? Alpha is austenite, and then your alpha is ferrite, and beta is cementine, which is Fe3C. So what happens in Eutectoid reaction? So Eutectoid reaction is this one where at some isothermal temperature of 727, your gamma austenite transform into two different matrix of alpha plus beta. So it transform into ferrite and cementine, right? And so basically it will be 727 degrees C. And if you see the carbon percentage, it will be 0.8%. 727 degrees C and 0.8% carbon, right?
Yes, sir.
Now, in the question 4, it says which of the following statement is correct regarding precipitation hardening. So, if we see precipitation hardening, what happens in precipitation hardening is uh, it's basically there will be a solution treatment. So, solution treatment is mainly you are heating to produce an elevated temperature single phase solid solution, and then whatever alloy you are producing, that alloy is quenched to prevent diffusion, and it produces a super saturated solid solution. So in case of non-ferrous material, which I will be coming in the next question, in case of non-ferrous materials, these super saturated solutions are often soft in nature, right? And then when you are quenching to prevent diffusion and making a soft material, or maybe in case of steel, you are making it in terms of martensite, when you are doing some rapid cooling after this solution heat treating, and then if you are doing some aging process. So basically in aging process, what happens, you are giving it some time and some temperature. So aging process is followed to provide diffusion and convert this supersaturated solution into some stable two phase structure. So if you are thinking of aging, there can be some natural aging which is done at room temperature, and you have something called artificial aging. So which of the statements are correct here? It says that in the first step solution treatment is produced. Yes, this is true. Sorry. And then supersaturated solid solution is developed through slow cooling. No, you have to do some kind of rapid cooling, otherwise it cannot form. Means it should retain the property at that temperature, right? If you are heating it at some temperature and then you are keeping it at some that temperature, maybe somewhere above that 727, which is the upper critical temperature, maybe say 800. So if you want to retain the property at this temperature, you have to do some kind of rapid cooling. Otherwise, if you are doing some kind of slow cooling, there will have some kind of diffusion and it can deteriorate the property of whatever you are gaining at this temperature, right? So if you're cooling it faster, that's what it called as super saturated. And then it tells that low temperature heat treatment is designed to reduce the yield strength. It is also false. Sorry, this is true, right? I mean, if you are doing some kind of tempering or this low temperature heat treatment, you're enhancing the ductility by compensating your strength property, right? And then it says longer times or higher temperature result in an increase in size of the precipitate and a reduction in both hardness and strength. This is also true. So if you are giving it more and more time, whatever precipitates will form in the matrix, it will try to grow, and because of that increase in size of that precipitates, there will be a reduction in both strength and hardness. Okay. So as I was saying that this question will come later. Which of the following statement is correct? If a non-ferrous metal alloy is quenched, the structure of the material becomes hard, the structure of the material becomes soft, it prevents diffusion or it provides diffusion. So whatever I covered till now, it's basically the structure for non-ferrous material will become soft and it prevents diffusion, right? So let us repeat it again. In case of non-ferrous alloy, if the alloy is quenched, it produces a supersaturated solid solution initially. And in this state, the material is soft for sure. For a non-ferrous metal alloy like maybe aluminum, copper, or maybe lead tin, whatever. And however, if the ferrous alloy is quenched, it creates the martensite structure because of the rapid quenching. And in this state, the material is very hard, right? And if you see the quenching of non-ferrous alloy, it prevents diffusion. Basically, what happens is like this: whenever you are increasing the temperature, so at high temperature, it is sufficient for dissolution of its soluble phases, right? So at high temperature, what happens is dissolution of soluble phases, and compounds which are then retained in solution by cooling rapidly from the solution treatment temperature. So you are heating and then you are doing quenching. So you are retaining that solid solution property, right? Compounds are retained in solution, and materials retain the properties of the solution. So what is the purpose? Purpose is to reduce the strength of the joint, or yes, the corrosion resistance also improve. With certain alloy, it may be followed by a lower temperature heat treatment again to reform this precipitates in a controlled manner, which I was calling it as use or precipitation hardening, right?
Yes, sir.
Now let's move to the next question. Need to match the followings of what is tempering, what is tempering, and what is forming. So if you see Ostem let us draw it here. Let us try to draw in terms of TTT curve. So this is your time, this is your temperature, and here at this 727, you have your detector temperature where austenite is stable, and then you have some kind of C curve like this. So this is your martensite starts, this is your martensite ends, I mean finish. And in terms of tempering, what happens? Say from here you are starting your cooling. You are cooling it like this at some temperature above that martensite start temperature, and then you stay it there. You stay there for a longer period of time, and then you cool it again. So what happens is basically, if you see tempering is it is used to reduce the crack uh, due to non-uniform cooling in different surfaces, right? Uh, so during tempering, it forms at constant temperature for sufficient time. So if you see it here, so it forms at constant temperature for sufficient amount of time. We say it long time, and bring what happens that during that time it brings uniform properties of fully austenitic matrix, right? And because of that uniform property, it actually reduces the crack since it forms at constant temperature. Uh, and maybe isothermal treatment at austenitic temperature, at which during the transformation is only benitic, right? So here, if you are cooling it and then staying it there, here you are forming only benitic structure. And what happen if you do further tempering? Further tempering of tempering steels are generally not required. So it is required for mar tempering. It is required for something called mar tempering. So if you want more toughness, more ductility, you want to do some step by step kind of tempering. So in terms of mar tempering, if you try to draw it, what happens is you have time scale, you have temperature, you have detector temperature, and then you are converting it. And now in terms of cooling, if you see, you cool it here and you stay it up to this much portion, and then again you cool it, you form some kind of martensite, and then again you temper it. So heating up to some temperature above the martensite starts, and again you stay it there, and then do some cooling, right? So this is maybe you call it secondary or additional tempering. So basically, if you are seeing mar tempering, so mar tempering is transformation of austenite into martensite, at the same time throughout the structure, right? So you're quenching from the austenizing temperature into a maybe hot fluid medium at a temperature above this martensite stud temperature, and then the cooling is stopped just above that martensite transformation region to allow sufficient time for the entire component to reach at that same temperature, and then again you are cooling and you continuing it at moderate rate, maybe through that martensite region. Moderate rate in the sense it can be air cooling, right? uh, and then it is followed by some usual tempering process to impart that toughness and better ductility. So in terms of tempering, this is step quenching, and tempering is also used to reduction of cracks. This forms at constant temperature for long time. For tempering, it enhances the ductility and toughness also. And now coming to forming. So forming is kind of a thermomechanical process which consists of simultaneously tempering, then rapid cooling, maybe some kind of deforming through cold rolling or maybe forging, and quenching to perform this shape and refine the microstructure together. In forming, you refine the microstructure and shape. Together. Now, it's basically it is heated from austenite and then quenching to the temperature between perlite and bainitic reactions. So wherever that reaction happens, so in between that temperature, you are heating that up to, and then it can retain its structure for a useful time. And at this temperature, maybe some kind of recrystallization occur and some degree of strain hardening occurs, and the resultant product, whatever you are getting from osforming, it has exceptional strength and ductility behavior. So it will be coupled with good toughness and creep resistance and fatigue life. So whatever osforming product you are getting, it has good toughness, creep resistance. Now, if you try to find out in terms of some kind of drawing, so it's basically this was your time, this was your temperature, this is ejector temperature, and let's say you are starting from here, you are heating the material above that upper critical temperature, and then you quench it rapidly, and then you do some kind of deformation at this state. Maybe you are doing some cold rolling operation or maybe forging, and due to this deformation, some kind of strain hardening as well. Recrystallization happens in the structure, and then after this deformation, you again do the quenching. right? This is what you get from os forming. Now this is the last question. So it's basically getting some basic idea of this, at which temperature region, at what time, how should be your heating rate, how should be your cooling rate, and depending on that you come up with different kinds of microstructures in between the same steel, right? So sometime if you are pulling it too fast, there will be martensite. You are pulling it too slow, and also the air medium or this water medium, this quenching medium also affects your cooling rate, right? So yeah. So in question 7, this also I already discussed, which of the following heat treatment process using a thermomechanical process to refine the microstructure and shape together.
Was for me.
Okay, this is osforming. Right?
Yes, sir. Sir, in the question 6,
Yeah.
for horse farming, what are the options that can go well, sir? Like
This
quenched
one.
between yes, sir.
Yeah.
And then is that like any other option will it go correct, sir?
Sorry, what happened?
It, what are the benefits of horse farming, sir? Like among enhancing ductility, toughness, or reduction of cracks, what we can get from apart from the microstructure? These will these two be an effect
So
of horse farming or
basically, heat treatment. Yeah, basically, whatever heat treatment you are doing is it's basically to control the microstructure only. To what should I say? To impart both strength and ductility in your material. So, like in martensite, if you are doing some rapid cooling, yes, it is increasing the hardness, but at the same time, also it is increasing the brittleness in your structure, right? So you have to do some kind of tempering after you are quenching to martensite transformation. Otherwise, it will be too brittle to use. So there will be no practical application of that brittleness in your structure. So you have to impart some kind of elongation behavior, some kind of yeah, this toughness thing. Like in case of additive manufacturing, also in case of, as I was the earlier day I was saying, in case of additive manufacturing also, you have so much of residual stress in your structure, right? So because of those residual stress, if you are using the material just after you are completing your additive manufacturing, this will be of no practical use. So in the material you have to do some kind of heat treatment to make it useful for practical applications. So most of the things are mainly you are enhancing the ductility somewhere, you are enhancing the hardness somewhere it is uh, much better, somewhere it is a little bit at lower side. So if you see in ostempering, martempering, so all are happening like you are doing some heating, then quenching, and then again tempering. Now it depends on your usefulness, what kind of property you want in your structure. So for that reason, in ostempering, you are going at some temperature different to martempering, right? So that depends on your application.
Yes, sir. So the doubt I have is for horse farming, will it enhance ductility or toughness, or it is basically
Ductility
majorly
and toughness are equivalent.
no, sir, because like in the match the following option, as you have written. fast farming will be helpful in increasing
Uh-huh.
the toughness and
Uh-huh.
grip.
Right, right. Yeah. Actually, if you see all these heat treatments now, except this martensite structure transformation, whenever you are doing some kind of tempering, some kind of uh, whatever temperature you go up to, whenever you are doing again heating the material and then means at lower side, some kind of tempering, it always imparts the ductility in the structure. So yes, horse forming also it will enhance.
Yeah, yes, sir. That's right.
And in that yesterday's session, not yesterday, that previous session, what was the, you remember what was the discussion we were having?
Yeah, yeah. Between IEV and PVD, sir.
So basically, iron vapor deposition is it's kind of physical vapor deposition. What I found, so you can take it in terms of maybe a subset.
Yeah, okay, sir.
It's both same kind. There is something called CVD, so that is a different case.
Chemical vapor deposition.
Yeah, chemical vapor deposition. There is difference in between PVD and CVD. But I found that yeah, iron vapor deposition and PVD, this is a kind of a physical vapor deposition.
Yeah, sir. The
Maybe
only
they
difference
have,
is we partially vaporize in iron vapor deposition. Just we
right,
don't go
right,
in PVD.
right. Yeah.
Yeah. Okay.
Okay. Is there any question more?
Clear, sir. Clear.
Yeah, you can stop it here then.
Sir, one more question. Like Mart
Ah,
tempering, one advantage of Mart tempering, as you said, is that we are quenching and we are also tempering it, so that the hardness is reduced and there is improvement in ductility. Because a martensitic structure will have it will be more brittle. So my question is, in that master following, as multiple options are allowed in this particular question, will it be applicable for the option called reducing cracks? Yes, it improves ductility and toughness. And what about the reduction of cracks? Like what is the basis, or what are the processes that will lead to the reduction of cracks? Is there any clear distinction between the properties which define reduction of cracks and the processes that differentiate crack reduction and enhancing the ductility or toughness?
yeah, means in terms of reduction of cracks, it may be like in ostempering. So in ostempering, if this is your temperature region up to what you are pulling it, and then you are keeping it at that temperature for a much longer time compared to what you are doing for tempering.
Yes, sir. Yes.
So because of that high time frame, uh,
High
maybe,
holding time.
yeah, high holding time. So maybe what happens that there can be some kind of diffusion happening, and because of that, if there is any kind of maybe I don't know, there can be some kind of volume shrinkage. So so basically, whenever you are having some kind of liquid and then it is getting solidified, so there will be some kind of shrinkage trends. because of that
Yes.
expansion coefficient. Now if you are giving it more time, so at that time maybe by that time maybe mm, whatever these trains are getting induced in between, uh, they get some time to heal. So there can be some kind of maybe crack healing due to high
Yes, sir.
amount of
Yes.
diffusion or high amount of time. I'm not sure, but yeah, maybe means my common sense says it's like that.
So we can consider like as in while we are doing horse tempering, the holding time is it is more constant and it is greater than
Yes, of course.
that of
So
mark
the
tempering. The
isothermal
crack
thing,
feeling will be much more prominent in horse tempering than that of mark tempering. Can
tempering,
we take it
right?
as?
Yes.
Yes.
So somewhere it is better, somewhere it is less better.
Yeah, yeah, yeah. Yes, sir. I get it. And also another doubt, sir. Like with the question we solve for non-ferrous alloys, where we have the diffusion, whether it prevents the diffusion or provides the diffusion. Can you just explain the three versus four, sir, and that of the properties that of non-ferrous versus ferrous while we are quenching? What happens regarding the diffusion regarding non-ferrous alloys and ferrous alloys?
So basically, in case of non-ferrous alloys, if you are doing some quenching, and even for ferrous alloys also, uh, when you are initially heating it up, so during heating, what happens that the compounds which are forming, those are retained in the solution if you're cooling it very rapidly, right? So it's like
Yes, sir.
what should I say, uh, you know eutectic, what is eutectic, right? So in eutectic,
Yes,
uh,
sir.
initially let's say it was liquid.
Liquid.
Let's say this is my eutectic. So initially it was all liquid, and then at this isothermal transformation temperature, uh,
Okay, alpha plus beta.
yes, so some kind of lamellar kind of structure will form. So
Yes.
it rejects the two phases. So if it is aluminum and copper, so it forms aluminum and Al2Cu. Two phases it rejects and it forms kind of lamellar structure. One is aluminum and this one may be Al2Cu.
Yes,
And
sir.
then with time, what happens? This if you are having lamella like this, with time it can grow, so it can be wider and wider. So basically, the idea is if you are not giving time for diffusion much, so whatever solution you are getting it here, it will retain the property because of it. Basically, it's not getting time of diffusion.
Rapid cooling. Okay, you don't give time.
So there is something called gradual cooling and rapid
Rapid
cooling.
cooling.
So in rapid
Yes, sir.
cooling, you are not giving time for uh, diffusion, and then means maybe you can think it of amorphous structure.
Okay.
So again, if we refer this eutectic, there is some concept of deep eutectic. So you are somewhere at this temperature region, and then if you are somehow able to cool it like let's say this is 600 degrees C, and you just an instant 600 to let's say 300. will there be any means if you are doing it just an instant, it will be there. The liquid, whatever property the liquid is having, that same property you will get at 300 degrees C. Means if you see how the glass forms, so it is just because of that rapid cooling only. There is no difference in between liquid and the glass form.
Okay.
No? So basically, you are not giving time for diffusion if you are doing it so rapidly.
Yes, sir. So, like again, reading the question, which of the following statements is correct? If a non-ferrous or metal alloy is quenched, means then, regardless of non-ferrous metal or ferrous, it will be preventing the diffusion only, no, sir, or will it differ accordingly?
It will be prevent for non-ferrous, especially. Yes,
Yes,
of
sir.
course, this will prevent diffusion, and for ferrous also it will prevent diffusion. But the thing is, for
Yes, sir.
non-ferrous, it will the structure of the material it becomes soft.
Okay. Okay,
But
sir.
in case of martensite, if you see, it will become hard and
Become
brittle.
hard.
Yeah,
Yeah, yes, sir. Yes, sir. That's the clear
that's
cut
the
difference.
difference. Hmm,
Yeah,
hmm.
yeah, sure, sir. I get it.
Anything more?
That's it. Understood. Understood. Yeah, got it.
Understood, now?
Yeah, sir, sure. I got it.
Yeah. Okay. Okay. Great.
That's
Great.
all.
Then let's stop it here. Then.
Yes, sir. Understood.
Okay. Sure. Bye bye.
Thank you so much, sir. Have a great evening.